The strong force. There is a reason the strong nuclear force is called strong, because in fact, it is the strongest force there is. In an atom, there exists in its center the nucleus, and within the nucleus, there is the protons and the neutrons. Now, these protons and neutrons exist within the nucleus and is believed to be held together with a strong nuclear force. Electromagnetic force is what keeps electrons in their orbit. For electromagnetism to be holding electrons surrounding the nucleus, then there must be something keeping the protons from escaping as well. It is known that the force of repulsion of two protons in the nucleus is newtons, and that is such a huge force for something as small as the nucleus. They should be repelling each other and flying apart instantly. The reason they are not is due to the strong nuclear force. Now, the binding energy of a strong force is so powerful. I'm not going to take you far. I'm going to take you into the scenes of Hiroshima and Nagasaki, the atomic bomb that exploded some time ago. That binding energy is the energy that keeps the protons and neutrons glued in the nucleus. It makes up 99% of the mass you see all around you. Only about 1% of the mass comes from the Higgs field, and almost all of it comes from the strong force. Now let's talk about quarks. Hadrons were believed to be the fundamental particles up until the 1960s, when quarks were discovered. Hadrons are a group of quarks. A group of 2 quarks is called a meson, and a group of 3 quarks is called a baryon. Initially, it was thought that there were only 3 kinds of quarks, which were the up, the down, and the strange quark. Then later, the charmed, the bottom, and the top quarks were all discovered. A quark is a fermion with half spin, charge of 1 on 3 or 2 on 3e, and baryon number 1 on 3. Strangeness is the description scientists gave to the new nature of attractiveness of the quarks, and that is why there is a strange quark. Now, the Pauli's exclusion principle states that no 2 electrons could exist in the same quantum state for fermions because they have different spins. And when we take the omega baryon, which is also a kind of baryon, it is made up of 3 strange quarks. So if you are talking about 3 instead of 2 for electromagnetism, does the Pauli's exclusion principle also apply for quarks? Yes, it does, but the difference is not dependent on spin like in the case of electromagnetism. These strong forces were then labeled red, green, and blue, and this brought about the concept of quantum chromodynamics. Yes, so different charges means different attractive forces. Since in electromagnetism there is the repulsive force and attractive force, these 3 quarks is what holds the protons and neutrons together in the nucleus. Quarks are matter particles and gluons are force particles. A proton is made up of 2 up quarks and 1 down quark, and neutrons are made up of 2 down quarks and 1 up quark. Both quarks and gluons possess the color charge, and I'll come back to the color shortly. These particles emit virtual photons, like we mentioned in the previous video, around them, forming an EM field, and this weakens the further you get to the nucleus. Gluons connect quarks. Flux tube is what we term as the gluon attractiveness or the gluon's tension, because the gluons, the interchanges of these quarks are so fast that they form like a solid tube called the flux tube. The constant exchange of gluons between quarks is what keeps these quarks bound together. The flux tube is the constant exchange of gluons, and it has a tension that stretches, and at a certain point the tube snaps to create a new pair of quarks. That is when the temperatures are very high and you are trying to separate these quarks. You form new pairs of quarks. If you break up a pair of quarks, you form new pairs of quarks. Color confinement is mostly always felt inside hadrons. Color confinement is the property of quarks to not be in isolation. So the color we are talking about is not the color that you see every day. This color is just a metaphor used to describe the properties of these quarks, what they exhibit. And then we are saying that these quarks can never be in isolation. There has never been an experiment where a quark has been isolated, that's left alone. These quarks are always in pairs or in triplets. Gluons are not like photons because they have two charges at the same time, a positive and a negative color charge, and they cannot be color neutral. There are no neutral gluons. Each color charge is equal to the negative sum of the other two. So for 2 we have red and anti-red, but for 3 we could have red, green, and anti-blue. There can't be a neutrality as in red, green, and blue. No, we have red, green, anti-blue, red, blue, anti-green, green, blue, anti-red. Red, green, and blue combine to form color white. The 8 gluons are red, anti-red, green, anti-green, and blue, anti-blue, white, and black, and this forms the eightfold way. The only fundamental particles that are affected by the strong forces are quarks, and the only particles that mediate the strong force are the gluons. The gluons mediate the strong force just as the photons mediate the electromagnetic force. Electromagnetism gets weaker when two charges get farther apart. Strong force, on the other hand, gets stronger when two particles get farther apart. It works like a rubber band. When an energy is great enough to break the rubber band, it creates a new quark anti-quark pair called a meson. And this is known as the color confinement. Mesons are formed, and they are the combination of quark and anti-quark pair. Color charges within nucleons are not perfectly balanced, not always. Not like the positive and the negative charges where there's a balance. There is always a residual force that exists. When two nucleons are closer together, this color residual force gets stronger, and this is actually the strong nuclear force. This strong nuclear force is mediated not by gluons this time, but by mesons within two nucleons. So when you have a snapping of this flux tube, that is the gluon um, interaction, it forms a quark anti-quark pair, and this quark anti-quark pair is a meson, and this is formed by the residual energy, and this residual energy is what we call the strong nuclear force. A gluon always has a color anti-color charge. For color charge to be conserved, when a quark emits a gluon, the gluon is absorbed by another gluon, and this quark experiences a color change. The color phenomenon operates just like color of your screen. There are packets of colors, red, blue, and green, called pixels, and this is what is responsible for the color combinations you see at different areas of your TV or phone. Same occurs in your eyes. In fact, humans have 3 color receptors, ones for red, blues, and green. Birds have 4 color receptors, dogs have 2, certain types of mantis has 16 color receptors. So to conclude, the strong force operates within the quarks, and the strong nuclear force is what mediates between 2 or more nucleons. This meson is stronger when the nucleons are closer together. Once again, this is Einstein in a Flash. Thanks for listening and watching. Until next time, bye bye.